In 1960, the computing pioneer Donald Michie proposed a way in which a series of matchboxes containing a large number of coloured beads could be taught, in inverted commas, how to play the game of Tic Tac Toe. Nowadays we would simulate this in computer code, but this was before the days of large-scale computing power, so Michie actually implemented it using a large number of real matchboxes and beads. The British call the game Noughts and Crosses, and so Michie named his system Machine Educable Noughts and Crosses Engine, MENACE for short. Here's how MENACE played Tic Tac Toe. Each of the 9 spaces on the board corresponded to a bead of a particular colour. Initially, all the boxes contained the same fairly large number of beads for each of the legal positions. Each matchbox corresponded to a particular arrangement of noughts and crosses on that board, and carried a small diagram on it to that effect. MENACE played a move by opening the box corresponding to the current ball position, choosing a bead at random to make its choice, and returning the bead to the box, recording the bead colour and the ball position that led to it in a list. Essentially, MENACE picked its squares randomly, depending on the contents of each box. If MENACE won that game, 3 additional beads of the colours in the list are added to the boxes. For example, if MENACE won a game in 3 moves by playing a red bead, then a green bead, then a black bead, 3 red beads will be added to the first box, 3 green ones to the second, and 3 black ones to the third. If MENACE lost a game, a single bead of the colours concerned would be removed from the boxes, and if the game was drawn, then 1 bead of the corresponding colours would be added to the boxes. This was because forcing a draw was considered an example of intelligent behaviour. In this manner, sequences of beads that led to winning or drawing moves became more likely, and those that led to losing moves became less likely. Michie wanted to show that blindly applying a simple set of rules could demonstrate intelligence, even though no actual intelligence was involved, and, indeed, with a bit of optimization, MENACE managed to win or force a draw against any player, however good, after playing fewer than 100 games. So here's my rather simplistic version of MENACE, and it comes to 179 lines of JavaScript code, link in the description. To simplify matters, rather than one player choosing to play noughts and the other crosses, the moves are marked C for computer and H for human. As such, we will need 3 images, all the same size. I've chosen to make them PNG images, C.png, H.png, and blank.png. The board is set up as a table in HTML. Each cell contains the blank image and is labelled with the name and ID attributes, numbering the cells from 0 to 8, that allow the JavaScript to refer to it. These numbers take the place of the colour code in the original MENACE. Each image also has an onClick attribute. You click on a square to choose it, and that triggers the function choose to detect a win or respond with a square choice of its own. The game also starts when the human clicks the first square, so the human has to go first. Diving into the JavaScript, we start with various variables defined globally so that all the functions can refer to them. The variables blank, computer, human, and game drawn are defined as 0, 1, 2, and -1 respectively for convenience. My convention is to define variables that I don't change throughout the program in uppercase letters. They're labels basically, to make the code more readable. The current state of play is stored in the array TTT for Tic Tac Toe, with element 0 corresponding to the top left corner of the grid and 8 to the bottom right corner, matching the name attributes of the images. Using the values of blank, computer, and human just set up, we can record any game at any state. For instance, the following board position will be recorded as shown. The board position is treated as a number in base 3, with individual digits that can be 0, 1, and 2. The multipliers are increasing powers of 3, which guarantee that all coded ball positions give a unique code number. Rather than a small picture of a grid on each matchbox, we can use these code numbers in a list of possible board positions, complete with a number of beads for each response the computer can make, like this. The collection of matchboxes is defined as an array called M-boxes, with element 0 corresponding to an empty grid, element 1 corresponding to a grid with an H in one corner, and so on. In practice, the majority of these entries will correspond to impossible board positions, such as a grid filled entirely with Cs. Including all the impossible ones, there are 19,683 possible board positions, and we save ourselves a lot of effort simply by defining the ones we need as and when they crop up, and leaving all the other entries in array mboxes undefined. Fortunately, JavaScript gives us a way of determining whether an element of mboxes is defined or not, using typeof, which returns either the type of the variable, if it exists, or the word undefined otherwise. We also define two arrays, which record the computer's choices at each stage of the game. Record pos is an array that holds the ball positions that MENACE faced every time it needed to choose a square, encoded as base 3 number. And record moves holds the square that MENACE chose for that position. The variable mv is used to step through these two arrays as they track the progress of the game. We have to track the game to tell MENACE which boxes to adjust afterwards, once it knows whether it has won or not. The variable winner holds the identity of the winner once there is one. While there is everything to play for, it holds the value 0. When the game is over, winner is set to computer, human, or game drawn. Let's track what happens when the human player clicks on a square. The function choose is called, with the parameter having the values 0 to 8 to specify which square was clicked on. If there isn't a winner, and the square chosen doesn't already have a C or an H in it, then the current board is updated by entering the value 1 for human in the appropriate square. The blank square is replaced by a letter H on the screen. At this point, MENACE checks to see if the human has won. After all, that click might have been the winning move. Assuming it wasn't, the computer must choose its own square in reply, using the function pickMove. Here is pickMove. First, we turn the current ball position into a base 3 number and store it in the variable idx. Then the function getEntry takes that number and uses it to extract a row from the array mboxes. Effectively, we are looking at the labels on the different matchboxes to see which one matches the current board position. The function countBeads opens that matchbox and counts all the beads in it. Then the function pickBead is used to choose a coloured bead from that matchbox. The bead is, of course, a number in the range 0 to 8, corresponding to a square, and the value is stored in the variable chosen. The screen is updated with the C graphic in the appropriate place, and the array TTT is updated to show that MENACE has made its move. Finally, checkWin is called again, this time to check whether the computer has won. The function getEntry deserves a mention. Its parameter is the row in the array mboxes to retrieve, and the first thing it does is to check whether the row exists. If it doesn't, then before anything can be returned, the row has to be created. It is set up as an array of 9 numbers, 0 to 8, each corresponding to a particular coloured bead. An arbitrary number of 10 beads is added for every colour that doesn't correspond to a space that is already taken by a move. Whether the row existed before or not, it can now be returned to function pickMove. Once the game is over, it's time to adjust the contents of the boxes that were chosen, and the function post-mortem does that. I'll assume you can go through the function checkWin for yourself to determine how it sets the value of winner to human, computer, or game drawn. Depending on that, post-mortem sets the value of the adjustment to +3, -1, or +1. It then goes through all the stored moves, adjusting the coloured beads for the matchboxes that were chosen. There are various other functions, such as save, load, and restart, but you should be able to work those out for yourself. And that is my stripped-down version of MENACE. Here are a few suggestions that you might like to consider to improve the code. The main problem with MENACE, as implemented here, is that it learns painfully slowly. Donald Michie streamlined his matchboxes by noting that many ball positions were rotations or mirror images of each other. By combining up to 6 ball positions into one matchbox, Michie managed to reduce the total number of matchboxes needed to 304. In our computer simulation, rather than rotating or reflecting the board itself before encoding it, it would probably be easier to use each game position to train up to 8 separate rows in the mboxes array. Moving further afield, can you think of any other competitive games that might be played by trained matchboxes. In theory, even a game like chess could be played this way, although the number of possible ball positions quickly explodes exponentially and makes such an approach impractical. Drafts, maybe. Well, that could be possible, although I think it would be very difficult to do. What about other games? I'll leave it up to your imagination. So, there you are. I hope you enjoy playing around with MENACE, and of course that you will subscribe, click the like button for this video, and leave a comment below.